All righty. Here we go. Whatever. All right, here we go. So this is a pretty thick packet, right? So chapter 5 is a really big chapter. Some of you guys kind of, when you saw this yesterday, like, oh my gosh, we still have this much more to go through. So yeah, this is a big chapter. It is kind of like chapter 3 was for derivatives. If you remember, it was a very long chapter. We had a lot of, kind of like topics to cover. But for the most part, we were building on things as we kind of went. And the same thing is true here. Yes, we're going to be covering a lot of topics, but they're kind of like all being incorporated as we go kind of thing. So it's not like we're learning little bits of things here and there, and you have to learn all these little bits. It all goes together, right? So that's the nice thing of it. But it still doesn't help that we have so much to cover. Anyway, so the two branches of calculus, differential calculus, that's what we were doing, right? Taking the derivatives of things, and integral calculus, all right, seemed unrelated. However, the connection between the two was discovered independently by Sir Isaac Newton and Gottfried Leibniz, I think is how you pronounce that. I looked it up on the internet, so it must be right. This connection is stated in a theorem appropriately named the fundamental theorem of calculus. Okay, so if a function f, believe it or not, there's also like a fundamental theorem of algebra. I don't know if there's other fundamental theorems, but there are like other fundamental theorems too. But anyway, if a function f is continuous on the closed interval from a to b, and capital F, right, that's our kind of like sometimes used way of denoting the antiderivative, is the antiderivative of f on that same interval ab, then the integral from a to b of f of x dx, that is a definite integral. The way we can evaluate that is by evaluating b, the upper limit of integration, in the antiderivative, minus a, the lower limit of integration, in the antiderivative. Okay? So we evaluate b in the antiderivative and subtract a evaluated in the antiderivative. All right? And so that's the fundamental theorem of calculus. Okay? Not that crazy. Maybe we already kind of figured duh, and not mind blowing there, but that is it. Okay? And so this brings together these two pieces, right? We've talked about indefinite integrals. We've talked about definite integrals, which we see right here, right, where we had to kind of like use that. We were using that to find the area under the curve and stuff like that. And now we have kind of like a way to evaluate a definite integral using our indefinite integrals, but then plugging in b and a there. Okay? So, guidelines for using the fundamental theorem of calculus, provided that you can find an antiderivative, right? Because there are still some functions whose antiderivative we cannot find, right? You now have a way to evaluate a definite integral without having to use the limit of a sum, right? Because we don't really like having to write that, but we need to know it, or geometric means, okay? These two things are still options, okay? Obviously, again, if you see a limit of a sum, like we saw in the homework and stuff like that, the idea is to pull from that what's necessary to then write the limit, the integral there. Or the geometric means, of course, we can still do that if we need to, again, using area formulas and stuff like that. All right. Instead, we're going to use this fundamental theorem of calculus. So when using the fundamental theorem of calculus, you use the following steps with the given notation. All right. So the first thing you're going to have is the problem. Okay. Sometimes you'll have to set this up. It's like a word problem, right? Sometimes you'll be given it. Just say, evaluate this. Then you're going to write equals. You're going to write the antiderivative here. Okay, so integrating the function f to get capital F. And then you're going to put that little bar here, that vertical bar, which means evaluated from a to b. And then you're going to write the antiderivative evaluated at b minus the antiderivative evaluated at a. All right? Depending on if it's a free response question or multiple choice, if it's free response, you can stop at this point. Once you've kind of plugged in b into your antiderivative and written then minus a evaluated in your antiderivative, you can stop, right? Because you don't need to evaluate arithmetic. If it's multiple choice, obviously you'll have to simplify and stuff like that. Okay? So those are our three kind of ideas here. And again, this is a way, if you remember here back from, if we have like our function f, all right, and we go from like a to b here, this evaluates and this finds, okay, that is this value right here. Okay? The upper limit minus that lower limit evaluating the antiderivative gives you the value of that area under the curve. Okay, that is the value of the definite integral there. Okay. So we can find the area of all sorts of weird shapes now without using necessarily, the typical geometry formulas. Although in a way we are just using a bunch of rectangles, an infinite number of rectangles added up, So, now, key thing to understand here, or not key, but like a little bit, not an idiosyncrasy, but anyway, something that happens, interesting thing that happens. It is not necessary for you to use a constant of integration C in this process. It is not necessary for use. All right, so anyway. I don't even know how I'm going to fix that, but you can fix it however you feel like it will work. Okay, so let's show you why that is. So let's say we got a random function here, f of x, and we're going to integrate from a to b with respect to x. Okay, and so again, the way we don't know what f is, but we denote its antiderivative as f of x, and let's put the plus c in. Okay, right? We're going to have some function, the antiderivative f of x, and we'll put in that plus c. And we'll evaluate it from a to b. Okay. And then we'll substitute in. So the upper limit of integration goes in first. So it's upper limit minus lower limit. So f of b plus c minus, and we'll evaluate the lower limit too. F of a plus c. Okay. Please make sure you put parentheses around these quantities, right? It's the upper limit evaluated at b, that quantity, minus the lower limit, okay, evaluated in the antiderivative there. So parentheses around that. It's the quantity minus the quantity, okay? What do we notice is going to happen with this subtraction, though? What's going to happen with the c's? They will cancel, right? Because when we distribute that minus sign, and this is a very common place where students, make mistakes here. That minus sign distributes to these terms here. This will be minus f of a minus c. These c's are going to cancel. And so we end up with just f of b minus f of a. So for a definite integral, it is not necessary to write the constant of integration because it is understood they will cancel out. For an indefinite integral, you better write the plus c's. And for the most part, you guys did a very good job on the quiz yesterday. I think just like, one or two questions. So like no one missed them on all the antiderivatives yesterday on the quiz. You guys did a really good job on that, so well done. Okay? Well done. Okay? All right, let's turn the page. The class average, I can tell you this much for the quiz. The class average for the quiz was like an 88. So it's pretty good. Pretty good. All right. Let's continue on here. Okay. All right, so let's try it. For our first problem here, evaluate the definite integral from 0 to 3 of 4x dx, so 4x with respect to x, using the fundamental theorem of calculus, and then verify by finding the area under the curve graphically. So we're going to kind of, again, just connect the idea that we can use the fundamental theorem of calculus, but in this case we could also still use that graphic, the graphing kind of area under the curve and using our area formulas and stuff. So let's do this the new way here. So the integral from 0 to 3 of 4x with dx with respect to x. Okay. When we integrate 4x, all right, we want to find that antiderivative. So the power for the x here is a 1. All right, we add 1 to our exponent, so we're going to get 4x to the 2. All right, and then divide by our new power, 2. Okay. I'm not going to put a plus c in. Okay, not necessary. We can simplify that if we want to become 2x squared. Okay, in fact, I'm going to do that just to make it nice. And then we'll evaluate it from 0 to 3. Okay, so this is like the only new part right here. And so we're just going to plug in, again, upper limit minus lower limit. So what do I plug in first here? The 3, upper limit, okay, minus, and then you can, well, I'll go ahead and do this just because. And then the lower limit, which is 2 times 0 squared. Okay. Be careful here when you're plugging in 0. Okay, the temptation is just be like, oh, it's 0. Well, the whole thing is 0. Be careful. Really, like, work through that part and make sure, convince yourself that it is, in fact, 0. Okay, especially when we start with ease and stuff. Yeah. Yeah, exactly. Zeros. Yeah, this is the easy class. Yes, she is.
She'll be like 2 minutes.
2 minutes? All right, Peyton, are you okay with that?
Yeah.
Okay. She's like, yeah, get me out of here. 4 minutes, 10, 20 minutes if you want. Anyway, okay. So So be careful, okay? Especially when we start working with e, right? E to the 0 is not 0, right? E to the 0 is 1. And so when you start plugging in those 0 lower limits, you might be tempted to say, oh, it's just always going to be 0. Well, not necessarily, right? Okay? Cosine of 0, right, is 1. So be careful when you're plugging in those zeros. Don't just assume that lower limit all cancels out to be 0. In this case, it does, right? 0 squared is 0 times 2 is 0. So the whole thing cancels out. We have 3 times 3, 9 times 2 is 18. Okay? And so there's our answer. Okay? This one, though, it was not necessary for us to use the fundamental theorem of calculus. We could have used our graphing method using geometry and stuff like that. So we'll say there's 1, 2, and 3. And let's see here. 3 times 4, I'm going to have to go up to 12. So let's go 2, 4, 6, 8, 10, 12. Okay. Let's all graph that just real quick here. Okay, there's from 0 to 3, so it's going to be, again, the area of the region between the curve. There's the curve 4x, between 0 and 3, and then also the x-axis is our boundary, so it is this region right here. Okay. This is a triangle, right? Area of a triangle is 1/2 base times height. What's the base of this triangle? 3. Okay, and then what's the height of it? This is a 12. So it's supposed to be 12. Okay. Yeah. So then that gives us 18 then for the total area. Okay, which matches to our 18 there, our answer. Okay. All good? So now let's try some more here. Okay. So letter A. Okay. Evaluate the following definite integrals. Okay. So no context given here, so we're just going to go ahead and evaluate these things. All right. So let's see here. I guess I'll do this just right down here. So we'll integrate t squared first, right? The integral of t squared, t cubed over 3, right? And then the integral of e to the t is, so minus e to the t. And then the integral of 2 over t, oh, okay, that's right. 2 over t is 2t to the negative 1. And so let's see here. I have to add 1 to the exponent, and so we get 2t to the 0 over 0, right? No, Mr. Widmeyer, no, don't do that. Okay, no, no, no. What is this integral? 2 natural log of the absolute value of t. Okay, now, I do want to speak to this a little bit. A few of us yesterday, more of us, so this was more of a problem yesterday. Please make sure you're putting in the absolute value of t there, okay, for that integral, okay? It is important in this case, all right? Whoops, I'm not going to put a plus c. And we're going to evaluate that then from 1 to 4. Okay, evaluated from 1 to 4. Okay, so we'll plug in the upper limit first. So it'll be 4 cubed over 3 minus e to the 4 plus 2 natural log. Now, with the absolute values at this point, if I'm plugging in a 4, I can kind of drop the absolute value, right? Because absolute value of 4 is 4. So I can just say natural log of 4 at this point. I don't need to then write the absolute value. If you want to continue to write the absolute value, that's fine, but it's not necessary. Okay, so there's the upper limit plugged in, minus, now we're going to plug in the lower limit, 1 to the 3rd over 3 minus e to the 1 plus 2 natural log. Again, absolute value of 1 is just 1, so you don't need to worry about the absolute values there. Okay, you can just kind of drop it. Okay, so 4 to the 3rd, right, is 64 over 3, so you get 64 thirds minus e to the 4th. Okay, and then let's see here, plus, I don't think there's going to be an easy way to simplify. So we'll say 2 ln of 4 minus, and then so I'm going to now distribute that minus sign, so it becomes minus 1/3, but plus e to the 1, and then minus 2 natural log of 1. Okay, let's see here. So what can we combine together here? Well, we have 64 thirds and 1/3. So we get 63 thirds. But then what is 63 thirds? 21. Okay, we have minus e to the 4th and plus e to the 1. Can those go together? Well, they both have a base of e, but if we're adding and subtracting, they're not like terms, right? So we can't add them together. So we have to put minus e to the 4th, and I'll just put a plus e to the 1 right next to it there. Okay, can Can we put together the 2 ln 4 and the minus 2 ln 1? Again, no, right? We're adding and subtracting. They're not like terms, right? Okay? We have 2 natural logs of 4. We have negative 2 natural logs of 1. They're not like terms. What is the natural log of 1, though, by the way? It's 0. So this just kind of goes away. We can then just have plus 2 natural log of 4. Okay. Remember your logarithm properties here. We could bring that 2 up into the exponent here and make it natural log of 16 if we wanted to, right? 2 times the natural log of 4 is the same thing as the natural log of 16. We could bring the 2 up, but it's debatable about whether that's more simple or not. So I'm just going to leave it the way it is right here. And that's our final answer. Of course, if this were a free response question, your final answer is right here. Okay, you do not need to simplify that. Please make sure you got the parentheses, though. Right? Please make sure you got the parentheses, though. All right. Questions on any of that? All right, let's move on then. All right, so now we want to find k. Find k where the integral from 0 to k of 2y minus 12 dy is negative 36. Okay, a little bit of a twist here now. So we're going to go ahead and integrate this. So integral of 2y, it becomes 2y squared over 2 minus 12y. We're going to evaluate that from 0 to k, and that's supposed to equal negative 36. Okay, right? Again, we're just going to integrate this. 2y is 2y squared over 2. 12 is minus 12y, and we have evaluate from 0 to k. That's equal to negative 36. So now we'll plug in our upper limit and lower limit. I'm going to go ahead and simplify the 2's, by the way, as well. So I'm going to get k squared minus 12k minus 0 squared minus 12 times 0 equals negative 36. Okay? So let's see here. Well, that lower limit is just going to be 0, so we'll be subtracting 0. No big deal there. Then we have k squared minus 12k equals negative 36. And how should we go about solving from here? What should we do? Yeah, we want it to be equal to 0, and then we'll factor. So k squared minus 12k plus 36 equals 0. That factors to k minus 6 times k minus 6, or really just k minus 6 squared. I don't know. I guess either one's fine there. And so what value of k solves this equation? 6. K equals 6. Okay, k equals 6 is our answer there. Okay. So we can even do these kind of like little twists on things, right? Which is not kind of in the same, way we've been going, where we're just like, here evaluate the integral. Here it's like, find this value of k that makes this integral equal negative 36, okay? And this is a kind of question that we could be asked and stuff too. So, all right, let's move on here. All right, letter C. Let's do this definite integral. All right. To evaluate this integral, do we have a quotient rule? No, we don't. So we need to simplify this integral before we then evaluate it here. So let's break it up, right? So we'll say from 1 to 4 of 3x to the 4th over x squared plus 2x squared over x squared minus x to the 3 halves over x squared, like that. And again, with respect to x. All right, I'm going to put that here, by the way. No quotient rule. So rewrite. Okay, I'm yelling at you because it's in caps. All right, and now we simplify. 1 to 4, 3x squared plus 2, and then 3 halves take away 2. Remember, 2 is 4 halves, so we get minus x to the negative 1 half. Okay. So we'll integrate now. All right, x squared becomes, or 3x squared becomes 3x cubed over 3 plus 2x minus. Does this become natural log? No, it's a negative exponent, right? But that's only when we have x to the negative 1, or 1 over x. That becomes natural log. This, we're just going to add 1 to our exponent here, just like we normally would, and becomes x to the positive 1 half over then 1 half. Okay, and again, we're going to evaluate that from 1 to 4. Okay, so we'll simplify here just a little bit. This becomes, that cancels out. I'm going to make this, instead of dividing by 1 half, we can multiply by the reciprocal of 1/2, which is 2. So we'll just say that's 2x to the 1/2 there. Okay, now we'll evaluate. So 4 to the third plus 2 times 4 minus 2 times 4 to the 1/2. And so then we will evaluate here. Again, 4 to the third, 64. 2 times 4 is 8. 4 to the 1/2, that's the same thing as doing square root of 4, right? So square root of 4 is 2, times 2 is going to give us a 4. Minus, and let's see here, 1, actually I'm going to do this all at once, I think I can. So 1 plus 2 is 3, and then minus 1 to the 1/2 power, 1 square root of 1 is 1, so minus 2. So it's 3 minus 2, which is just then a 1. Okay. And then follow your order of operations here, right? So 64 plus 8, right? 72. Minus 4 is 68. Minus 1, 67. You have just addition and subtraction. You evaluate from left to right. Left to right. All right. Let's do this last one here. And why don't you guys go ahead and try this one? Of course, the trig one, Mr. Witt. What a jerk. All right, well, you guys go ahead and try it out, and then I'll do it. I'll lag behind just a little bit. Okay? It's not crazy. Just do it. Just do what we've been doing. Just do what we've been doing. Okay? So, I guess I'll go ahead and do it too. Okay, so there it is. Again, if this were a free response question, you could stop right there, including not evaluating tangent of pi over 4 and cosine of pi over 4, right? If it's free response. But if it's not, you need to be able to evaluate tangent of pi over 4 and cosine of pi over 4, okay? So understand that, right? You need to be able to evaluate that trig stuff, right? And you really need to make sure that you have down those trig integrals too. Okay, for those of you that were fuzzy on your trig derivatives, you're going to stay fuzzy on your trig integrals. Okay, so you need to know those. Okay, backwards and forwards, right? Because the derivative is kind of like, I guess you could say forwards and then backwards for the integrals and stuff. Okay, all right, moving on. All right, so now our directions change ever so slightly. We want to find the area under the curve of each of the following functions from 1 to 4. All right, so how are we going to do that with this? What should we do? Take the integral. Okay, great idea. We're going to integrate from what to what? From 1 to 4, right. Okay. And we'll do the square root of 4 over x. Maybe we should rewrite that, right? Because we don't like having those root symbols. We never really use the root symbols when it comes to taking a derivative or taking an integral. So let's rewrite that. We can break up a square root over a quotient like that. And so you can say then this is just 2 over the square root of x, or we could say it's 2x to the negative 1/2. And so we will do that. 2x to the negative 1/2 dx. Okay, it's helpful to rewrite there to make things easier for ourselves. All right, so now we'll integrate, right? Add 1 to our exponent here, so we're going to get 2x to the positive 1/2 over 1/2. Evaluate that from 1 to 4. 2 divided by 1/2 there, right? What does that simplify to be? 4. So I'm going to make that 4x to the 1/2. And so we just evaluate here. So 4 times 4 to the 1/2 minus 4 times 1 to the 1/2. Okay, so we get 8 minus 4, which is 4. So the area under that curve, from 1 to 4, whatever the oddly shaped region that's going to be, it's going to be a precise value of 4. Okay, 4 units. Again, depending on our units. 4 units squared, I guess I should say. All right. Now, of course, we can't go too long without talking about piecewise functions, everyone's favorite. So we'll do the same thing here. We're going to evaluate the area under this curve from 1 to 4. Okay. But of course, piecewise functions are made up of more than one function. Which one of these functions are we going to be integrating here? Good answer. Trick question. Both of them. All right, both of them we're going to be integrating here. So how can we integrate 2 functions over this interval? Any ideas about how we should do that? What should we do? Sean?
You should integrate both and put the 1 into the first one and the 4 into the second.
Okay, integrate both. Put 1 in the first one, 4 in the second one. Close there, close. But by doing that, we're only evaluating... I guess I see what you're saying there. That's something we can do. What we're going to do here is kind of like a little bit more, but right idea there. We're going to break up this integral here. Where does our function switch? At 2. So we're going to integrate, and it doesn't matter, kind of, I guess, which one you put first here. Let's see which one does. Okay, doesn't say, yeah. Yes. All right, so we'll integrate from 1 to 2. Okay, we'll integrate from 1 to 2 of what here? The 2x squared minus 5, because that's for the values that are less than 2. So 2x squared minus 5. And then to that we're going to add the integral from what to what? 2 to 4 of 2x minus 1. So you see we break up the integral here. Okay, and that's all there is to it, right? So piecewise functions don't have to be so scary. We just break it up into 2 things. Yes, it's more work, but it's not so scary, right? And so then we integrate here. And we end up with 2x to the third over 3 minus 5x. And we'll evaluate that from 1 to 2. Plus, and then we end up with 2x squared over 2 minus x, evaluated from 2 to 4. Okay. And let's see, does anything simplify nicely? Yeah, we can get the 2's to cancel at least. And so we'll plug in our upper limit here, so we'll have 2 times 2 to the third over 3 minus 5 times 2. Oh goodness, I hope I left myself enough space, but I don't think I did. Okay, so there's my first evaluation. I'm going to add to that then 4 squared minus 4 minus 2 squared minus 2. Whew, just barely fit. Kind of had to shrink it down there after a while, but there you go. Okay, so this is a bit tedious. right? And it's easy to like drop a negative or miss a parenthesis or drop a power or something like that. Please be careful, right? Please be careful. This will test your attention to detail here. So watch out, okay? If you miss one little negative sign or you miss one little number or one little substitution, it's going to throw everything off. So please be careful here, all right? Maybe I don't need to tell you that, but I'm just going to say it anyway. So 2 to the third is 8, so we get 16 thirds here. Minus 10 minus, let's see here, that's going to be 2 thirds minus 5 plus 16 minus 4 minus 4 minus 2. Okay, so let's see here. I'll go ahead and distribute the minus sign here as well. So we get 16 to negative 2 thirds, so 14 thirds minus 10 but plus 5 gives us minus 5. And let's see, 16 minus 4 is 12. Take away 2, so 10. So you get 14 thirds plus 5, which is really 15 over 3, which is 29 over 3. Okay, so 29 thirds. 29 thirds. Okay, questions on any of that? Again, the challenge there maybe not so much the calculus, more like the algebra potentially, or like the arithmetic even, I would say. Okay, so just be careful. All right, so now let's add on another kind of additional concept to our fundamental theorem. So we are going to talk about the average value of a function on an interval. All right, average value. All right. We've already talked about the average something before, but we know how to find the average what? Rate of change. Okay, so I'm going to write that here so we can kind of compare. Average rate of change, if you remember, was f of b minus f of a over b minus a, the slope of the secant line. Okay? So the secant line. For the average value of a function, so not the average rate of change of a function, I should write that part here too. Okay? For the average value of a function itself, if f is integrable on the closed interval ab, then the average value of f is 1 over b minus a integral from a to b of f of x dx. So what's the only difference here? You put this 1 over b minus a in front. Okay? The 1 over b minus a in front. Okay? So we're going to find the average value of f of x equal to 3x squared minus 2x over the interval from 1 to 4. Okay? So we're finding the average value of f. We're not asking to find the average rate of change, right? If it said average rate of change, then you do f of b minus f of a over b minus a. We're asked for the average value, so we're going to use this formula right here. 1 over b minus a. So our b is 4, our a is 1. This will be 1 over 4 minus 1, integral from 1 to 4. Watch your order there, okay? Please be careful, right? b minus a, but the integral is from a to b. From a to b. From 1 to 4 there. Okay? And then of our function, which of course is the 3x squared minus 2x dx. Okay? It's up to you with what you want to do with this 1/3 out front here. You may distribute the 1/3 through the problem and then integrate. That's fine, okay? Because this is just a coefficient. So you could distribute the 1/3 through the integrand and then integrate it with that. Or you can integrate what you've got here and then just distribute the 1/3 through it afterwards. So it's kind of like up to you how you want to handle things here. I'm going to leave the 1/3 out front and integrate it as it's written. So we'll have 3x to the third over 3 minus 2x squared over 2, and then evaluate that from 1 to 4. Okay, so I'm going to rewrite this one more time here. The 3's will cancel, but now we're going to have 1/3 x cubed. The 2's will cancel, but we'll have 1/3 x squared. Again, evaluated from 1 to 4 there. Okay, and so we can just plug in now. Remember that 4 goes into both x's here. Both x's, right? 4 goes in here and here for that upper limit evaluation. Minus then, 1 goes into both the x's, the lower limit evaluation there. Okay, so let's see here. We get 64 thirds minus 16 thirds minus 1/3 plus 1/3. Okay, so the lower limit ends up canceling out. All right. So that's fine. Okay. And then 64 minus 16 is going to be 48 thirds. But that simplifies further to 16. Okay. Average value over the interval from 1 to 4 is 16. Alrighty. Let's take a look at something here real quick. 2x squared minus 2x. Window 1 to 4. Okay, so just to kind of give you, oh, question, yes.
So like I'm still trying to understand like what exactly we're finding here.
Okay.
Like on the graph, like what would it be?
Okay, so let me answer that. I actually have like a picture right here. I was going to do that for you. So if you'll permit me here to just kind of show you here kind of what this is. All right, I'm going to graph 3x squared minus 2x and my y1. Okay, which is the function whose average value we're trying to find over the interval from 1 to 4. I'm also going to graph 16, the average value of that function from 1 to 4. And then I'm going to be a little more careful, or not tricky here, but like I'm going to adjust our window too. We're only interested in the interval from 1 to 4, so I'm only going to graph from 1 to 4. And then I also had to adjust the y because the graph didn't quite fit. All right, so there is the graph. Okay. So what you can kind of imagine this to be, okay, is so you have all of these different values of this function from 1 to 4, right? So all these different y values, okay? 16, well, if you look at it, where is it located? Roughly in the middle of all those values, right? You have all these values below it, all these values above it, and so 16 is the average of all of those infinite number of y values averaged together, yeah.
What would that be used for?
So it just depends. We'll actually see it show up in some contexts here later. So if you want to hold off on that, we can kind of see it. But it's like anytime. Let me see here. How can we see it? So like for example, if you have a certain car or like a particle or something like that, and you have its velocity function, you can then find what its average velocity is over a particular interval and stuff like that, which is helpful, for whatever kind of situation. But that is a quick example kind of thing. Just a quick number to compare it. Yeah.
When I was evaluating it for the average value, is it okay for me to just leave the 1/3 or like 1 over b minus a, more generally speaking, like in front of the whole, like all the math, and then
Like did you had like the 1/3 out front here, and then a big set of parentheses around the whole.
Pretty much.
Yeah.
I solved it like.
You did everything in here with a 1/3 out front, and then you had 48, 1/3 times 48, and then did that. Yeah, that's fine. That's fine. Yep. As long as you have the correct, grouping symbols and stuff like that to show that you're multiplying everything by 1/3, that's no problem. Yeah. It's kind of up to you where you want to put it and stuff. So yeah. All right. Enough of that then. So. Example 5, I'm looking forward to this one because it's going to give us a nice kind of like connection between average value and average rate of change. We're going to do this question using both methods, okay? They are related, right? And I'm going to try and show that to you here using those two different methods. So we've got a position velocity acceleration function here, or a problem, I guess. A ball is fired from a cannon, and its position can be modeled by the function that, okay? Find the average velocity of the projectile over the interval from 1 to 3 using two different methods. And those two methods, the two methods we know for finding the average of something is the average value and the average rate of change. Okay, now, before today, if we're given the position and we wanted to find average velocity, okay, if we were given the position and we wanted to find average velocity, what would we have to do? Or what would we use here, I guess, in this case, before today? Okay, so we could, well, would we use the derivative, though? If we want to find the average velocity, what is the velocity again? It is the rate of change of the position. So we could say average rate of change of position here, right, instead of velocity. Okay. So if we want to find the average velocity and we're given the position, we're going to use the average rate of change formula. So, let me see, I want to make sure I write this right. Okay. So we're given position, and we need to find velocity or average rate of change of position. Okay, so we're given the position. We've got that. We want to find the average velocity. Oops. Find average velocity or the average rate of change of position. Okay, we would use the average rate of change formula. So we could find this by doing f of b minus f of a over b minus a. Or I guess I shouldn't use f's there. I should use positions. Sorry. So it should be like s of b minus s of a. And this is where it got confusing, right? We're being asked for average velocity, so the temptation, right, is we should use velocity for this. We should use velocity, right? But no. The formula we had in the past was average rate of change. So when we're asked for average velocity, the velocity is the rate of change of position, so we actually need to use position here. We actually need to use the position, right? And this was confusing for us because we had to take that like kind of extra kind of like logical leap, or that, you know, kind of like reinterpret what the question was asking every single time. So this is just going to be s of 3 minus s of 1 over 3 minus 1. Okay. Which you guys can find that, so I'm not going to worry about calculating it out here. I'll just have it. I have, you know, a pre-prepared kind of like it calculated out. So 10 minus 42 over 3 minus 1, which is just 2. Okay, which gives us negative 32 over 2, which gives us then negative 16. Okay. We don't really have units given to us here, so we're not going to be able to give units. Okay, but there would be our average velocity using the old method. Using that kind of confusing way, we have to reinterpret. Average velocity means the average rate of change of position. So given the position, we're going to use that. Okay. Now, for today's method, if we want to find the average value, if we want to find the average velocity, okay, we need to start with velocity. So given now the velocity, we need to find the average value of velocity. Okay, so if we're given the velocity and we want to find the average velocity, we're going to find the average value of the velocity. So now is when we would take the derivative of the position. So we get s prime of t, which is equal to v of t, okay, which is negative 32t plus 48. Okay. So it is this that we're going to apply our average value to. So we'll do 1 over b minus a, so 1 over 3 minus 1, times the integral from 1 to 3 of the velocity here. So negative 32t plus 48 dt. We'll do it with respect to time. Okay, and so we'll integrate this thing. So we'll have a 1/2 in front times, and then that's going to be negative 32t squared over 2 plus 48t. We're going to evaluate that from 1 to 3. So we're going to have 1/2 times negative 16t squared plus 48t. Okay, and then again evaluating from 3 to 1 there. So 1/2. Actually, I'm going to distribute the 1/2. So it'll be negative 8t squared plus 24t. Okay. When all is said and done, this should equal negative 16. Okay, when all is said and done there, that will equal negative 16. Okay. So you can see kind of two different ways of doing this. Okay, and I mean, you can kind of see what's going on here. I mean, what did we do here? We did position minus position over 3 minus 1. So 10 minus 42 over 2, negative 16. What did we do here? Well, we found the velocity by taking the derivative of position, but then what did we turn right around and do with the velocity? We integrated the velocity, which gets us back to what? When you integrate the velocity, what do you end up with? Position. And what are we going to do? We're going to evaluate the position at 1 and at 3 and subtract those and multiply by 1/2, or in other words, divide by 2. So you can see we end up doing almost the exact same thing here, okay? Just 2 different ways. All right. Let's press on here. So example 6, the function f is continuous for negative 4 to 4. The graph of f, shown to the left, consists of 5 line segments. What is the average value of f on the interval from negative 4 to 4? Okay, so let's think about this here, right? To set this up, it'll be 1 over b minus a, so 4 minus negative 4, times the integral from negative 4 to 4 of the function f of x with respect to x. Now, we don't know what the actual function f of x is. In fact, it's going to be piecewise, right, based on all those different parts and stuff. Okay. But how can we use this graph to help us evaluate this integral here? What can we use? What can we do? What's that? Break it into the different pieces and then use area formulas, geometry. Just find the areas of these little spaces and these regions. Okay? So don't forget the 1 over 4 minus negative 4, which becomes 1 over 8, right? So this thing here, right, represents the area under f from negative 4 to 4. Okay? So that representation then, we just need to find all those little areas and add them up. Well, I should say area under f above x-axis 2, okay? And so we just want to find all those little areas, add them up, and then multiply by 1/8, okay? So let's do that here. So let's see here. This first triangle from negative 4 to negative 2, right, it's got a base of 2, height of 1. So 2 times 1 is 2. Half of that will be 1. Okay, this next triangle right here, okay, its base is 1, 2, 3. I guess I can write these in here. So that's area of 1. This next triangle right here has a base of 1, 2, 3, height of 2. So 3 times 2 is 6. Half that is going to be 3. But of course, since it's under the x-axis, we should make that a what? Negative 3. Okay. And then let's see here. I'm going to cut this next region into kind of two pieces. It's like right here. Just because it's not like one shape we could use here. So I'll do this triangle. So it's a 2 by 2 triangle, which is 4, but half of that is 2 for the area. So plus 2. And then this last little shape here, what's that? A trapezoid, right. And so it's a 2, 1. So let's see, and the height is 1. So it'll be 1/2, 3. So 3 halves is the height there. I guess you can also just count the squares. There's 1 full square here and a half a square here, so 1 1/2. 3 halves. You could do it that way too. Okay? So we add all this up. 2 plus 1 is 3, plus -3 is 0, so that's all 0. So it's 3 halves times 1/8. 3 halves times 1/8? 3/16. La-da dee. Okay, one more here. Last one. Oak marked. Oh, by the way, that little CA stands for calculator active. Okay, for our class. Oak marked creates a model to fit the monthly sales data for their top selling product, out of sight, out of mime, a street performer repellent. Mr. Goff came up with the street performer repellent. He doesn't like street performers. So, anyway. The model is S of t equals t squared over, you can talk with him about that if you have it next semester. T squared over 4 plus 1.8 times the square root of 2t plus 1 plus 0.4 sine t pi t over 6. Okay? Thank goodness this is calculator active, right? So, over the interval from 0 to 24, where S is sales in thousands and t is time in months, find the average sales. So, are we supposed to use average rate of change formula here or average value formula here? We're given the sales, and we want to find the average sales. So it's average value. Average value. So it's going to be 1 over 24 minus 0. Okay. Now, why are we going from 0 to 24 if it's asking for the average sales over 2 years? Because, right, t time is in months. Okay, so we're going from 0 to 24 here. Right. And then from 0 to 24 of t squared over 4 plus 1.8 square root of 2t plus 1 plus 0.74 sine of pi t over 6 dt. All right. So get your calculators handy. Alternatively, if you guys want to save time, you don't need to write out the entire function or the entire function here. You could just say 0 to 24 of s of t. That is perfectly legitimate. Okay, for your your setup. Okay, please make sure you are showing your setup though. But that's fine. You don't need to, do all that. Okay. We have two options here about how we type this into our calculators. Okay. Option 1, for those of you who maybe have the newer calculators and stuff like that. Let me see if I can get a bit up here. Like that, okay? If you press, well, first of all, make sure that your mode is set to radians, okay, because we do have some trig in this. It's going to set things off. I'm teaching geometry too, so I have to switch between degrees and radians. I think some of you guys in physics have to do the same thing, so anyway. Then we go to math button, and I believe it is, well, for me it's number 9. Okay, so the math button, number 9, FN int, stands for integration, right? Okay. And I get this very nice picture here. Okay, so some of you with older calculators, you don't get this, and I apologize. All right, I can show you how to do it with your older calculator too, but we'll do it this way here. So 0, 24, and they're going to type in our function. So x squared over 4 plus 1.8 square root of 2x plus 1 plus 0.74 sine of pi x over 6. Okay, and then I have to put an x in there for the dx. And then you hit enter. I think it's safe here because there's only one term, the x squared, and then divided by 4. Is it wrong to do that? No. If you want to put parentheses on it, it's a good habit to be in. But in this case, I think it should be okay. Okay? And so there's my answer. No. I have to multiply by 1/24 still. Don't forget that 1/24 out front. and it's 56.55 is our answer here. 56.55, what are our units? Thousands, right? S is sales in thousands, so it's thousands of sales. It's a very popular street performer repellent. Well, it's 2 years sales. I don't know. I guess there's not that many street performers though, so I guess some people carry it just for, you know, in case, just in case. It's just a spontaneous street performer. Okay. Now, of course, you can avoid having to do that times 120. You can put the 124th out front in the very first place, then do math and number 9, and then you can type it in, all that jazz, you know. So if you want to, you can do it that way too. You don't need to like forget the 124th until the end. You can put it out front at the very beginning and then do your integral that way. Okay. For those of you that don't have the pretty type like I do, okay, no fear here. I will show you real quick. You can still type the 124th times. You'll do math, again, fn int. Okay. The first thing you're going to type in here is the function. So it's going to be x squared over 4 plus the 1.8 square root of 2t plus or 2x plus 1 plus 0.74 sine of pi x over 6. Then you're going to put a comma. Okay? And then this comma, it separates, we're going to put another argument in. We're going to integrate this with respect to x. So comma x, and then comma, now you're going to put your lower limit and upper limit of integration in. So 0, comma 24. Okay, isn't that beautiful? All right, there it is. And now if you hit enter, oh, I hope I didn't make a mistake. There it is, 56.55. Okay? So again, for those of you with order calculators, it's math, oh gosh, I forget, math 9, okay, and then fn int of the function, comma, variable, so x there, comma, lower limit, comma, upper limit. Okay, so A, B, F. Okay, those of you with the order calculators. My apologies for those of you that do have that, but there it is. Okay. Please make sure you type this in your calculator and get the same answer, right? Please make sure you're able to type it in. Okay, I know it seems kind of silly, but please make sure that you're able to type that in because you don't want to mess that up, right? This should be easy points. Or you don't want to have like all the calculus, right, and then just mess something up because you can't type in your calculator accurately. Okay. Questions on any of that? All right. Well, that's all I've got for today. So the homework is posted to Google Classroom, so you can get started on that. I'm going to pass out the pile of papers that I've got here, including your quizzes. Okay. So you can see those. Yeah. Oh, question on the calculator? Sure. Okay.
So my calculator, I don't have it with me again, but I have a TI-84 that only lets me do it like that. Like, how did you change it from your first way to the second?
Mode button,
Okay.
and then if you have math print as an option, but not all of them have that option. Okay. So, yeah. So absolutely. So I'll show you if for one other option here, folks. So let me show you one other option here. Okay, another option that you might want to use again for those of you with the older calculator. Okay, you can type in this function into your y equals. So you can do x squared over 4 plus 1.8 square root of 2x plus 1. Plus 0.74 sine of pi x over 6. So you can type that in, okay? And then you have some options here as well about what you want to do. You could go back to our previous method and use the fn, ooh, not there. Well, I guess I should turn this back to not pretty type anymore, right? All right. So you can go back to that. You can use bars, y bars, function, y1. So you don't have to like retype the whole function again. You can use just y1 there. You can do comma x, comma, 1, or it was what, 0 to 24. Okay, you can do it that way. And then divide by 24. Right, the 1 over 24 there, so 124. Or you can go into your graphing section of the calculator. Oops. You can do this with the graph. You need to make sure, though, that in your graph that you've got the interval from 0 to 24 on your graph. So I'm just going to go up to like 25 here on my x. You can do second trace, and you see here for number 7 there's an integral f of x dx. And so I'll just kind of wait for that to show up. Just got a graph first before you can do anything. And then notice it's asking, what is the lower limit? So the lower limit is 0 for our case. The upper limit is 24. And you can actually see it. Find the area under the curve. Again, that number you then multiply by 1/24 or divide by 24. Okay? And I think, again, if you have a new calculator, if you immediately from this answer, if you hit divide by 24, interesting, yeah, because of a rounding, I guess, error there. It gives you 56.549999, which is just 56.55, the same thing there. It'll take your answer from the integral, and then you can just use that too. So that's your another option there too. However you want to use it. Okay? So, sorry, now you're free. My apologies. Thank you for that quick pause there. So, get you these quizzes back. Yes.